dozen or not very many. Instead of going into the statistical analysis, which I will talk about a bit later. I have an example here of the Comp128 GSM algorithm. Excuse me. And we've taken two traces here. Now we see the power is going up and down and something's happening here. But there's actually something interesting happening here. We see that the processes up to here are aligned. So they're doing the same things. Then here in between, something happens and they start misaligning. So you'll see that this process is actually a bit quicker than this one. And after that, they go do the same thing again. Now, in this case, we had the source code of this algorithm. And we found in the C source code that a byte was being taken from a table of 512 entries. And this depended on two other bytes, so K and D. And K is actually the secret key that's being used. So that's the thing we're after. And D was just input data. So that's stuff we controlled, stuff that we could send out to the card. But why the hell would a table lookup, which we matched up to this part, be non-constant? It's just a memory indexing. Well, that's because this was run on an 8-bit microprocessor. So effectively, it cannot index into a 512 entry table. So what the compiler does, it looks at this C code and says, oh, that's not going to fit. So it basically splits the table into two 256 entry tables. And then runtime, it will decide, do I look in table A or do I look in table B? And that's what we can see here. So there's actually a bit of time difference depending on which table it's indexing. Now, that's all very fine, but what are we going to do to break this? Remember, we control D, and we want to know K. So we basically start off by sending D0, and then we send D1, D2, etc. So in the first case, we'll stick to these shorter traces. And at some point, at some value for D, we will see that it's actually jumping to the other table. So at that point, we know K plus D equals 256. So we've effectively broken the key there. So here you can see that even at all kinds of different levels here, you don't see any problem with the code. And when you go down deep into the assembly level, you will see that these kind of timing differences start to occur, and you can break the whole security of a thing by that. So that was more on simple power analysis, which only works if you have very leaky cards. So basically, if you look at one trace, you can see the differences. So this is typically what we would see. For instance, this is a software DES. So it's executing on a card, and it's calculating a DES. We're going to zoom into this a bit. What you see here is the initial permutation for DES guys out there. This is the first round, second round, third round. It goes on, but I left that out. We're going to zoom into this part. We see this pattern occurring. I'm going to zoom in a bit further there. And then we actually start seeing some interesting differences. Here I've plotted 16 traces on top of each other. And you can see that they're sort of the same power level here. And here you start seeing something's happening. And here even they're going wild even further. And that's when we start cheering in the lab, when we see something like this. Because this is actually the data influence. So actually the fact that a byte has a different data value gives a different power value. That relation, that's bingo. For us, that's profit, I guess. Now that's great. We don't see that anymore because nowadays manufacturers know about these kind of things. So we typically get more traces like this. It's just one big band of noise. So you have to go into more statistical methods to actually analyze these kind of things. So the question is, where is this data being processed in all the noise that we have? So before we could just zoom in and find the different power levels and then deduce the data. Typically it's actually leaking the Hamming weight of the data. So it's actually leaking the number of bits that are set to 1. basically because the assumption is that every bit has the same influence on the power level. That's just an aside. So the question is, where is data being processed when you're in the presence of noise? Well, in this case, we take many traces. So we take a lot of these measurements. And for each measurement, we also register the data that we send to the card. And typically what we would do if we're analyzing, for instance, an AES implementation or a DES implementation, we send out random input data. So it's uniformly random. And of course, we know the data that we send to the card. We know the data that's coming out, but we don't know the secret key. So that's what we're after. What we're going to do is we're going to focus on one bit of one variable in the process. Now, this sounds a bit complicated, but for now, let's just presume we're looking at the first bit of the data block that we're sending as input. So it's either 0 or it's 1. So by looking at this bit, we can group all our measurements into two big bins. One where this first bit of input is set to 0, and one where it's been set to 1. Next thing we do is we take these big bins of traces and we average them. So we end up with 2 traces. And the interesting thing is that the only difference between these 2 traces, the only statistically significant difference between these traces, is the fact that these bits are different. Because all the other bits that we send, they're uniformly random, so they're not correlated with this one bit that we're looking on. So the only statistical difference that we've made here is that one bit being processed. So if we subtract these traces, we're actually going to see noise, except in the places where this bit has caused some kind of influence on the data. And this is very strong, because we don't always take 1,000 traces. Sometimes we take 1,000,000 traces. So we can detect differences in voltage in the tens of millivolts. It's amazing. And it's very hard to protect against as well. So that's what's called a differential trace. So it's a trace that shows sort of over time, it gives peaks on where statistically this one bit that we're looking at has caused an influence on the power. So the input for differential trace is just n traces with some known variable. It can be input, output, anything else, but you have to know it. And the output is a trace like this. Now this actually is the thing that I ran on the DES again. And what you see here is, so it's the first bit of input to the DES algorithm. So that will correlate here during the initial permutation where the bit hasn't been changed yet, but it's just being shifted around. And then later on it will correlate in the S boxes, and the correlation actually goes down, because that's what a crypto algorithm does. It decorrelates the input from the output. Now, that's all great, but what if we don't know the value of the variable for each trace? Well, basically, we're screwed. You need to know the data. But it's not as strict as that. It also works if we know that the data might be restricted to some set of, some collection of data. So, for instance, let's say we've taken, well, in this case 4, but n traces, and we know that the data is either 0, 1,